A hydropower turbine worth millions of dollars can be slowly destroyed by something smaller than a grain of a rice. A single stone the size of a grain doesn't look dangerous, but inside a hydropower plant operating under a 420 meters head, water is compressed to nearly 4 megapascals of pressure and accelerated to tremendous speed. Under these conditions, that tiny particles become a high-speed projectile. Each impact is like a microscopic bullet striking the turbine steel surfaces. And it doesn't happen once. Millions of sediment particles slam into turbine blades, guide vanes, and other critical components every single day. Over time, these tiny impacts can carve away steel, reduce efficiency, force costly shutdowns, and shorten the life of equipment worth millions. So, how do engineers stop an entire river full of sand and rock from destroying a hydropower plant? The answer is a series of clever engineering defenses that begins long before the water even ever reaches a turbine. Let's follow the journey of water through a run of river hydropower plant and see how engineers fight back against sediment. The battle against sediment begins long before reaching the turbines. It starts at the intake structure at first, and the first line of defense is surprisingly simple. Rather than drawing water directly from the riverbed, engineers position the intake at higher elevation. The reason is straightforward. The heaviest rocks, gravel, and coarse sediment travel close to the bottom of the river. By placing the intake above this zone, engineers can capture cleaner water while allowing larger particles to continue downstream. Think of it like taking water from the top of a muddy bucket instead of scooping from the bottom. But the intake elevation is only part of the strategy. Notice that spillway is located lower than the intake. This creates a natural pathway for sediment-laden water to keep moving through the river. Heavy particles follow the low route, bypassing the power plant altogether. To better understand, let's first see a spillway rail gate open after a year located at the bottom of the dam. You can see how much silt has gathered at the river bed during this period. Even before the water enters the system, gravity is already helping engineers separate sediment from the flow. The second line of defense is the reservoir itself. As the fast moving river enters the reservoir, its velocity drops dramatically. And when water slows down, it loses its ability to carry heavy particles. One by one, sand, silt, and other suspended sediment cling towards the bottom. To take advantage of this natural process, the intake structure is built on an elevated concrete platform. Most of the heavier sediments settle in front of the intake, forming a sediment trap instead of continuing into the waterways. In a way, the reservoir acts like a giant settling basin, quietly removing a large portion of the sediment before the water ever reaches the turbine. But the problem doesn't end there. Over time, these trapped silt can build up and block the approach to the intake. That is why engineers installed powerful undersluice gates beneath the intake gate. When these gates are opened, high velocity flow rushes through the bottom of the structure, picking up the accumulated sediment and carrying it away. The muddy water is then discharged through a dedicated gallery and returned to the river downstream. Thousands of tons of silt can be flushed out, keeping the intake clear and protecting the entire hydropower system from excessive sediment entering the waterways. But rocks aren't the only threat. Rivers carry all kinds of unwanted passengers, branches, logs, leaves, and vegetations, even entire trees during flood. If these objects enter the tunnel, they could block flow, damage equipment, or interface with the turbine operation. That is why the next defense is to remove these floating debris. For logs and floating debris, there are multiple defenses installed in a hydropower project. One is a floating log boom, which you can see here as a red line, which keeps large floating debris to reach the intake portion and is placed such that these debris are diverted towards the spillway side. When the logs and floating debris becomes too much, the flap gate is operated and these floating debris are flushed back again to the river natural flow. Then right in front of the intake gates are installed large trash stacks. These steel bar acts like joint filters, water flows through, large debris stays behind, simple, reliable, and absolutely essential. So these trash racks are choked over the time with small floating debris like plastic trash coming from upstream. So to clean the trash rack, engineers have designed and installed a trash rack cleaning machine at the intake portion. This intake trash rack cleaning machine cleans the trash racks using a grapple. But even after the logs and branches are removed, the most dangerous threat is still hiding in the water, tiny grains of sand. They are far too small for any screen to catch. To stop them, engineers need something much smarter. They need to change the physics of water itself. This is where the real magic happens, the sediment trap. After passing through the intake, water enters three enormous sedimentation basins. At this point, the water is still moving fast, and the fast moving water can carry huge amount of sediment. So engineers do something that seems almost too simple. They slow it down. The channel suddenly becomes much wider. As the flow spreads out, its speed drops dramatically, and that is where gravity takes over. Think of it like a crowded hallway. If everyone is running, everything stays in motion. But when everyone slows to a walk, the heavy stuff naturally settles down. The same happens here. As the water slows, the heavier and silt particles can no longer remain suspended. They began sinking towards the bottom, minute after minute and hour after. Layer after layer of sediment settles onto the basin floor. Meanwhile, the cleaner water remains near the surface. No pumps, no motor, and there is no complex machinery. It is just gravity doing all the hard work. And but this creates another question: if all the sediments settle to the bottom, where does it go? So engineers can't allow sediments to keep building up forever. Eventually, the basin would fill completely. So hidden at the downstream end of these basin is a powerful cleaning system. Along the bottom, there are 12 flushing gates. These gates have one job: remove sediments. When operator open them, a powerful rush of water sweep across the basin floor. Years of accumulated sand and silt can suddenly surge out of the basin and back into the river. It's like pulling the plug from a giant underwater vacuum cleaner. Within minutes, enormous quantities of trapped sediments can be removed. The basin is cleared and the turbines remain protected. But that flushing gates aren't the only gates here. Above them is another set of 12 outlet gates. So these gates handle something much more valuable: clean water. Remember, most of the sediment is now sitting on the bottom. The cleaner water remains near the top. So these outlet gates collect water from the upper portion of the basin and directs it towards the headways tunnel. The dirty water stays behind, the clean water moves forward. A simple idea with a massive impact on turbine life. After leaving the sedimentation basin, the cleaner water enters the headways tunnel. From there, it travels towards the penstock and finally it reaches the turbine. But by now, the water has already passed through multiple layers of protection: the raised intake structure, the lower spillway, the trash rack, the sedimentation basin, and the flushing system, and the carefully positioned outlet gates. Each defense removes a different threat. Each stage makes the water cleaner, and together they protect some of the most expensive equipment inside the entire power plant. Because in hydropower, generating electricity isn't just about moving water; it's about controlling it. And sometimes the biggest engineering challenge isn't the water itself; it's the tiny grain of sand hidden inside of it. So this is the first episode of sediment removal technique in our hydropower project. In the coming series, we would be looking how engineers remove the silt back in the early days from 1935. And also we will cover more run-of-river projects located on canals and barrages and see how they remove the sediments.